Okay. Quit that. All right. So we're talking about chapter 5, and the difference between chapter 4 and chapter 5 is this. In chapter 4, what kind of probability distributions did we work with? Discrete or continuous? Discrete. So what do you figure we need to work with now? Continuous. And when they are continuous, we usually call them standard normal distribution, or at least normal distributions. We're going to talk about the difference between when it's standard and when it's just a normal distribution. Now, here are the properties. First of all, they apply to continuous random variables. So if you remember, one of the examples we talked about when we discussed the difference between these is when you can divide whatever it is you're measuring into separate sections or pieces or portions and it's meaningful, that's when it's continuous. Like when you're filling up your car, how many gallons are you putting in the tank? It doesn't have to be a whole number of gallons. You can have a portion of a gallon. Hours spent studying in a day. It could be anywhere from 0, let's hope not, to 24. That would be bad too. Okay. So anytime we have a continuous probability distribution, that means that the random variable was continuous. Now, normal distributions, we've actually talked a little about these before. It is a continuous probability distribution for a random variable x. It is the most important continuous probability distribution in statistics. If you take a higher level statistics class, you will discover there are other types of distributions that you will probably study. We won't do them in this course, but the normal distribution is very useful. And look at that graph. Does that thing look familiar? Yes, it is symmetric. What do we call that curve? It is bell-shaped. So you remember talking about this before, right? Remember the empirical rule? Oh, taking you way back to chapter 2. If we have a certain number of standard deviations from the mean, according to the empirical rule, we would know the percentage of data that would be within one standard deviation of the mean, and 2 and 3 and so forth. So we're going to kind of review some of that stuff, but we're going to go into more detail with normal curves. Now, if it's a normal curve, this bell-shaped curve, the mean, the median, and the mode are all the same, right? And it occurs at the peak or the high point of the curve. We know that means that it is symmetric about the mean. I'm going to have, basically, if I'm looking on the left side of the mean, so if I'm looking over here, what percent of my data would be to the left of the mean? 50%. Excellent, 50% of the data. That would mean to the right of the mean, that's where the other 50% would be, because the total area under the curve is how much? 1. Think about what 1 is if you change it to a percent. 1.0 turns into 100%. There you go. All right. And what we do know is that as we move away from the mean and we get out here to these tails, the curve gets closer and closer to the x-axis, but does it ever actually touch it? The answer is no. It won't actually touch it, but here's what we discussed. Let's see what you remember about the empirical rule. If I move 1 standard deviation from the mean, do you remember what percent of the data would be there? 68. Okay, if we're 1 standard deviation from the mean, then yes, about 68% of the data would be between 1 standard deviation below and 1 above. What if I'm 2 standard deviations from the mean? Do you remember that one? 95%. Once I got 3 standard deviations from the mean, I have what percent? 99.7%. Is that darn near everything? I would say 99.7% is darn near everything. But here's the deal. As we get out in these tails, we are leaving this tiny, tiny, tiny possibility that there could be some data out there. There's not going to be much, but I don't know where it would be. So that's why it never actually touches the x-axis and closes the thing off, okay? But for all practical purposes, by the time I've gone 3 standard deviations, I've gotten most of it. So here's the other thing that I don't think we talked about last time. If we did, bear with me. I want to remind you about it. I'm going to tell you, you won't have any questions where you have to identify this necessarily in the homework or on the test, but this is sort of good to know. In fact, we're covering this right now in Math for Business too, as we're taking things and we're graphing them and we're talking about important features of a graph. And so what we are looking at is called concavity, the concavity of a graph. Now, what does it mean if something is concave? All right, it describes the shape of the curve, right? So any contact lens wearers in here? All right, see if you relate to this. Before you pop that contact lens in your eyeball, do you look at it on your fingertip? Sometimes, really? Okay, I always look at it because does it matter which direction it goes on your eyeball? What happens if you put it on the wrong way? Okay, that's a nice way of putting it. It feels weird. If you ask me, I say it really hurts and I want that sucker out as quickly as I can get it out. Because here's the deal. When we talk about putting it on the right way, if you're putting your contact lens on correctly, this is going to be the shape of the curve of the contact lens. What would you tell me about concavity? Does this look concave up or concave down? It's concave up. It means it's like a bowl that's sitting up that if I poured water in it, it would hold water. So if you think about like a pet bowl and you're pouring water into it, if it's turned that direction, it is concave up because it would hold something. Now, if you put your contact lens in backwards, what happens is, yeah, this part's like this, but the outer edges do this. They get this inflection point and the outside edges aren't concave up, they're curving down. That's why it hurts, because it's sticking into your eyeball, your eyelid, once you put it in. So where you have a change in concavity, where something goes from being concave up to concave down, or vice versa, is called an inflection point. Now, looking at this curve, like I said, don't stress over this. You're not going to have to answer it, but I want you to recognize when you get one standard deviation away from the mean, what shape would you say the center part of the curve is? Concave up or concave down? That's concave down. That's like an upside down water bowl. You know, your dog's going to get really thirsty. You can't get any water if it's been flipped over upside down. But notice what happens when you move past this point. What does this end look like? That's concave up. It's like half of a bowl that's turned up, all right? But the curve itself would be concave up. Is the same thing true on this side? Yeah. So anytime that your curve changes from being concave up to concave down, that's called an inflection point. And on these normal distributions, that point occurs one standard deviation away from the mean. Okay, that's where the natural inflection point will occur. Now, if it's a normal distribution, your mean can be anything and your standard deviation can be any positive number. These are just things to remember. I mean, because we've talked before about if I were working at the zoo and I wanted to get the mean of the weights of all the elephants, I could do that, right? And then I could calculate their standard deviations. But those numbers would look very different from, say, collecting the data then on the flamingos, all right? The mean will tell me where the line of symmetry is located. Doesn't that make sense? As long as it's a normal distribution, when I find the mean, I'll know where the line of symmetry is. But what the standard deviation does is it describes the spread. Now, see if you remember this from talking about it before. If my standard deviation is very small, what do you think it does to my data? compared to the mean? Does it keep the data close or does it spread it out if the standard deviation is very small? Keeps it close. So what do you think that's going to do to my curve? Is it going to make it kind of skinny? Okay. What if my standard deviation is pretty large though? Then it spreads out the data and I get a curve that's more wide and it will cover more area. Okay, so look at this. What you should notice is on each of these graphs, your inflection points are occurring one standard deviation away from the mean. Now, if I compare this graph and this graph, what do you notice about their means? What would be the mean here? 3.5. What would be the mean here? So the means are the same, but would you say the shapes of these graphs are the same? No, because what does it look like the standard deviation would be here? If I'm going from 3.5 to 5, that's about what? 1.5. But what would my standard deviation be here? Because I'm going from 3.5 to just a little past 4. It's certainly no more than 1. It might even be less than 1. So this one, B, has a smaller standard deviation. That's why this data is clustered closer to the mean than the other one. Does that make sense? Now, if you compare B and C, would you say that the mean is the same on these? No, because the mean is 3.5 here, but what is it on this one? But what does appear to be the same? The standard deviation. So what do you recognize about the shape of those graphs? Do they look the same or different? The same. So that standard deviation is going to tell us about the spread. So if the only difference was where the mean occurs, it's the same shape graph. It's just moved over to wherever the mean should be for that particular set of data. The fact that the means are the same doesn't have any bearing on whether the shape of the graph will look the same or not, because the standard deviation is going to affect the shape. All right, does that make sense? So standard deviation tells us about the spread of the data. Now let's see if you can answer this. Which one would you say has the greater mean? Curve A or curve B? Because what do you think the mean is on A? Looks like it's about 15. What do you think it is on B? And so because 15 is larger than 12, I agree. Curve A has the greater mean. Now, which one do you think has the greater standard deviation? Why would you say that? It's spread out wider. Very good. B has the greater standard deviation because A is not as spread out. Okay. Scale test scores for the New York State Grade 8 math test are normally distributed, and the normal curve shown below represents the distribution. Do you think you could estimate what the mean test score is? Now, again, this is a little bit on the goofy side because this is kind of hard to see, but let's just kind of see if we can figure out a reasonable estimate. This is 650, 660, 670, 680, 690, 700. What would you say you think the mean might be? 675. Okay, we think it's halfway between 650 and 700, so we'd say 675. Now, this would be the part that would be very difficult to eyeball. Estimate the standard deviation. So by looking at the curve, what we're trying to figure out is where would that inflection point be? Where would it go from being concave down and start becoming concave up? So if I'm moving along this way, you tell me when you think we hit that point. Okay, I got one person who said now. Y'all agree or should I keep going? Okay, so that looks pretty close at where it might shift from concave down to concave up. So from 675 to wherever this is, you think that's about how many? Looks like it might be around 710, so about 35? 35, 40, somewhere in there, okay? You guys are pretty good. You actually did a pretty close estimate. We definitely got the mean right at 675. And they've got the standard deviation at about 35. Does So kudos, very good. Okay, yeah, if only you got paid for that kind of skill, huh? Okay, standard normal distribution. When it is a standard normal distribution, this goes back to when we worked with z-scores. Remember the whole purpose of changing something to a z-score? We did a question that compared, I think, when Heath Ledger won Best Supporting Actor and when Penelope Cruz did. And we were trying to decide, comparatively speaking, because there was a different mean for the age of actors winning Best Supporting Actor compared to Best Supporting Actress and a different standard deviation. We had to change them to z-scores to be able to figure out which one actually was youngest, relatively speaking. So that's what z-scores do. If I had all of those weights of elephants and all of those weights of flamingos, I could change them into z-scores to see which one might be relatively, I guess, have more change that's happened if one of them has tended to gain more weight than the other or something. So this normal distribution means we changed it to a z-score. And if it's a standard normal distribution, the mean is always what number? If it's a standard normal distribution, the mean is always 0. And the standard deviation is always 1. Okay, that is a given. Now, the z-score, if you remember the formula, we did this at the end of chapter 2. Whatever value of x you have, you would subtract the mean from it and divide by the standard deviation. And that's how you convert it into a z-score. So you can make those comparisons. And they've given us this little graph where if the mean is 0 and the standard deviation is 1, you've got 1 standard deviation on each side, 2, 3. By the time you're at -3 and +3, we said according to the empirical rule, that's what percent of the data? 99.7. We are just almost to the point we've got it all, but not quite, okay? So what we want to do is take x values, change them into z-scores so that we would be able to work with a standard normal distribution. Now notice, remember how we looked at that graph a little bit ago and we said that if you didn't change your standard deviation, basically you're keeping the same shape, right? So if all we're doing is converting it into a z-score, this is going to be exactly the same shape. But instead of maybe having a mean at 215, we'll make the mean at 0 and the standard deviation will always be 1. And then we can work with it a lot easier, okay? And that's why you're going to need that table that I just gave you. I'm going to show you how you can read values in the table. Now, there's actually a couple of different ways you can calculate these probabilities or these areas. The table is one. I'm going to show you in the calculator a little later too. Now, here's the part where I mentioned sometimes when you put things in the calculator, you may be off by 1/10,000. I never had this problem in the old textbook that we used to use, but this textbook, there must be something a little different in their table. Because it says that if you go to -3.49, all right, so we've gone a little more than 3 standard deviations. It's saying when you're at about -3.49, you ought to have basically an area of 0. Because remember, we're always going to be identifying the area that goes to the left of something. So if I'm all the way on this end of the graph, I basically don't have anything between the graph and the x-axis, right? What do you think is going to be the area if I go all the way out to like 3.49? It should be very close to what? 1, exactly. I should have almost all of the area under the curve when I move out that far to the right. Now, if I stop at the mean, that makes sense that the area would be 0.5, right? And then here's where we said if we go all the way out to 3.49, our area would be close to 1. Okay, now this is your table. And here's how it works. First of all, do you notice that it's two-sided? If you haven't, pay attention. One side has positive values, the other side has negative values. So let's look on the side that has positive values. And you guys kind of follow along with me. Because if I change my data to z-scores, let's say I've got a z-score of 1.15, and I want to know, bless you, the area to the left of a z-score of 1.15. Here's how this table works. My z-scores are going to be in these outer rows and columns. So I start by going down this column until I get to, now it'll go to the nearest 10th. So I want to stop at 1.1. So I come down to where 1.1 is. Have you found that on your sheet? Mm-hmm. Then go across the top rows until you get where? 0.05. And where these two intersect, that's going to be the value of the area to the left of a z-score of 1.15. So here's how you read it. There's 1.1. There's 0.05. That's where those two intersect, and I get an area of 0.8749. Make sense? Mm-hmm. Not hard, is it? What does that mean? Okay, so what that would tell me is if my standard deviation is 1 and my mean is 0, which is what happens if I'm using a z-score because I've made it a standard normal curve. If I mark 1.15, that would tell me that if the whole thing has an area of 1, I have 0.8749, that much area to the left. If you want to think of it in terms of percent, I got almost 87.5% of the area to the left of that. Okay?
This tells me it's not very good. It's not very close.
Well, it just tells me that this thing is like, okay, let me give you an example. Some of you maybe have taken something like an SAT score recently. Maybe, maybe not. Did you take one a long time ago? Okay, so if you took an SAT test and you get your scores back, it will tell you what your actual score is. Like maybe you made 1250, or maybe you made, I don't know, some other number, which might mean something to you, might not. But what is it that kind of helps you know how well you did? They also tell you your what? Percentile. So if you got a percentile score and it was 87.5, what would that tell you? That's right. You did better than 87.5% of the people who took the test. So that's kind of the same concept here. If we're talking about we have that much area to the left, then that means that there's 87.5% below it. So depending on what you're talking about, if it's SAT scores, that's probably good. I'd feel better about myself if I know I did better than 87.5% of the people who took it. Okay? Now, if we're talking about survival rates for 5 years after a cancer diagnosis, and this has to do with the likelihood that you won't make 5 years, that's not going to be a good thing. All right, so it kind of depends on what your data is telling you, whether you're going to think that's a good score or not. But basically, it's going to have 87.5% of the data below it. Okay, now let's look on the other side of your chart where the negative numbers are. And do you see something that looks a little funny about it? Which way does it count? Instead of counting up, it counts down. Look at this. It starts with negative 3.4 at the top, and it's going down. And look at these. This is the part that you got to be really careful about. It goes from 0.09 down to 0.00. So you got to make sure you don't let that trip you up when you start to read values. So let's see if you would get the cumulative area that corresponds to a z-score of negative 0.24. So in other words, if I had a bell-shaped curve, and I know that the mean is 0, standard deviation is 1, and I want to know how much area is to the left of a negative 0.24, okay? I can find it in this table. So, you guys found it yet? What do you think the value is? 0.4052, is that what I heard? Okay, because if we go down to negative 0.2, we go across to 0.04, you guys got it. All right, so does that make sense? And here's what you got to make sure you don't forget. Anytime I'm reading these values out of the table, it will always be area to the left of the number, okay? Because guess what? Sometimes they ask you to find the area to the right. So we'll have to make sure we know how to do this. Now, if you're finding areas, here are the steps you want to make sure you take care of. First of all, even if you think you can do it without doing this step, I am going to look for this on your test. Please do what I did on the board. Sketch the curve and put the value on there and shade the area you're trying to find. One of the reasons that's going to be most helpful is it makes you pay attention to whether I'm looking to the left or to the right. Okay, so you want to make sure that you draw yourself a little bell-shaped curve, shade the area that you're trying to find. As long as I'm looking for area to the left of a z-score, it will be the value I see in the table. But what do you think I'm going to have to do if I want area to the right of the curve? Subtract it from 1. Very good. That's all you have to do, but you got to remember to do it. So if I were looking for area to the right of 1.23, I would look up that value in the table. It would be 0.8907, but that's the area to the left. So in order to get the area to the right, I'd have to do 1 minus 0.8907, okay? And if I need to find area between two z-scores, guess what I have to do? I got to look both of them up, and then I would have to subtract. So I would take the one that's furthest to the right, which is going to give me all the area out to this tail, and then I would have to subtract out this area, and that would give me the area in between. All right? Give me a quick signal. Does this make sense? Yes, or no, or maybe. Okay, we are going to practice this. So, looking at your sheet, can you find the area under the standard normal curve to the left of a z-score of negative 0.99? Negative 0.99 area to the left. Found it? All right, so if I were to ask you what you think it is, somebody tell me. 0.1611, how many of you got that? Okay, that looks good. And that's what we're looking for. And that is the answer because we needed area to the left, and that's what the table tells us. Now, can you find area under the curve to the right of z equals 1.06? And yes, it's okay to use your calculator if you need to. So did you find the value in the table? What was it? 0.8554, right? But that's actually the area that's to the left. So how do I get the area to the right? 1 minus that, and that gave you what number? 0.1446. All right, how many of you got that? Very good. Now, on this one, you'd have to look at both numbers and subtract. And I'm pretty confident you can do that based on the answers you've been giving me. Would you like for me to show you how you could do this in the calculator? Okay, you don't have to do, in fact, I have a number of students who decide they really would rather use the table, and that's fine. but let me show you what you can do. And there are times that the calculator will really be handy. And I think anytime you've got between two curves, that's when it's going to help the most. So if you have one of the calculators and you want to follow along, here's where you go. Where did we go when we wanted to do the binomial PDF? So this is also a distribution. We'll go to second bars, but we're not working with a binomial probability distribution. We're working with a normal, and that's right at the top. So we don't want normal PDF. We want a normal CDF because this is a cumulative distribution. Remember, we're getting all the area to the left of some value. So here's what we do. Now, the lower limit, if you have one of these calculators, it may already have defaulted to this. You know how we said that if you went 3 standard deviations, you had 99.7% of the data according to the empirical rule? When I taught this using that other book, when I told you I didn't have as much trouble with things rounding correctly, we just went from -4 to +4. Wouldn't you think as long as we're past -3.5 and +3.5, we ought to have it? Well, that doesn't work as effectively with this table for some reason. So what I'm going to tell you is this. You might want to type in like -100 for the lower end. Basically what we're saying is we want to go from the tail. In fact, let's do this when it's on the board. Let's say we want to go from this tail all the way up to a -0.24. So when I'm typing this in, I'm always going to go from left to right. So I could, what this is saying is it's going to be like a -0.0000 whatever. I'm just going to tell it I want to go from -100. And my upper is going to be that -0.24. And then it asks me for the mean and the standard deviation. As long as I'm using a z-score, mean's always 0, standard deviation is always 1, okay? So I don't have to change those. If you were typing this in and you didn't get this screen, then you probably wound up with the normal CDF, the parentheses open, and then you've got to make sure you type it in this order. You want to type in that lower boundary. So we're going to put in a -100. You type in the upper boundary, which was -0.24. By the way, you're separating all these with commas. And then you got to tell it the mean is 0 and the standard deviation is 1. Now if I hit enter, I've got 0.405. Oops, you know what? I need to go back and change my mode because I had changed it to 3 places. I want it to float. So I get all of those. So I've got 0.405165, da-da-da-da-da. And that would mean, because if you look in the table, all of these go 4 places to the right of the decimal. This would be what? 0.4052. Now, if I compare that to looking at the -0.24 here, my -0.24 was right there. Right there, 0.4052. So you can find it in the calculator if you wish, or you can read it off of the table. Now, where it's really helpful, in my opinion, is one like what we just had up here on the board. And I'm going to tell you what those values were. You were wanting to find the area between a z-score of -1.5 and +1.25. So if I go back into second bars, and I choose 2 for normal CDF, I'm going to put in the lower boundary, which is the smaller of those 2 numbers, -1.5. My upper boundary is the positive number, 1.25. And then I'm not having to look up 2 values out of the table and subtract. The calculator will take care of all of that for me. And I'm going to get 0.82754229, da-da-da-da-da. Now, if I have that, what would this round to if I go 4 places? 0.8275. Now, let me show you when we go back here to the screen. All right. So if you were to look this up in the table, what does it tell you the z-score is for 1.25? Can you find that real quick? 0.8944. And then if you flip over and you look up the area that goes with the z-score of negative 1.5, what do you get? 0.0668. If I take the difference between those, I am off by 1/10,000. Okay? Because we got 0.8275. That's going to be 0.8276. Now, typically, the computer does give you 1/10,000th grace, so it would probably count right 0.8275, 0.8276, and 0.8277. But if you typed in 0.8275, it counts it wrong and says it's 0.8276. That's when you want to send me a message, because I would look and I would go in and check it in my calculator, and if I get that same number, I'm going to give you credit. In fact, if we were to change this to, I'm sorry, what?
You made it where you not type it down in. What did you get? Second.
Oh, if you do second enter, it'll pull back up and it will let you edit. Okay. So technically, what we're doing in the calculator is actually more precise. The reason it's off just a hair is because they rounded the 1.25 that's showing up with 4 places in the table, and they rounded the negative 1.5. And so when, kind of like you guys were talking about, if you're adding or subtracting those rounded values, you actually can be off a little bit. Ours is more exact, but if I'm reading it off the table, that's what happens occasionally. Okay? Now, that's everything that's in section 5.1.